stays live. So
yeah. I think I. Huh. What?
wait, what? I'm so confused.
Oh, okay. Wait. I see it. Yeah.
Is it live? Hello.
Yeah. Okay.
Okay, cool. Okay, sorry about that, technical difficulties. So for anyone who's watching online, can I just get all of you to scan this QR code and fill out the form? Okay, so welcome to part 2 of the 2601 revision seminar. For this seminar, we're going to cover these 3 topics. So geometric properties in SVDs, canonical Jordan form, and matrix exponentials. Okay, so starting off with geometric properties and SVDs, we have our first definition, which is what is a rotation matrix. So we define a rotation matrix R to be denoted by R of alpha to be of this matrix here. And in here, we can say that e to the I alpha is basically an eigenvalue of the linear map T. And this basically describes a rotation by alpha about the origin. Similarly, we can kind of extend this idea into 3-dimensional spaces. So if we consider some matrix Q to be some 3x3 orthogonal matrix, so that its columns they form an orthonormal basis for R3, then we say that Q is unitarily similar to one of the 2 matrices. So the first matrix here has the one at the top left corner. This indicates that it is a rotation. And the second matrix here is very similar, except now we have the -1 in the top left corner, which indicates that it is a reflection. So yeah, pretty straightforward. And we say that for rotation, the determinant is equal to 1, and for a reflection, the determinant is -1. Okay, so now we have some theorems relating to these matrices. So I guess for an orthogonal matrix Q, we say that if the determinant Q is equal to 1, then Q is unitarily similar to equation 1, so this matrix here, as I've said before. And if the determinant Q is equal to -1, then Q is unitarily similar to 2, so this matrix here. Now for next theorem, we say that for an orthogonal matrix Q similar to the first matrix here, alpha can be found by solving this thing here, which is the trace. Now recall that the trace is basically just the sum of the diagonal entries. So if you, for example, take the sum of these entries, that is the trace. And using this formula here, you can find the angle. And similarly for the second matrix, you can also do the same thing, except instead of the 1 at the beginning, we now have the -1. So if you take the sum of the diagonal entries, you should also be able to find the angle. And this is just kind of, I guess, reinforcing what I said before, right? We can say that the eigenvector corresponding to eigenvalue 1 is basically the axis about which the rotation matrix acts. And for an orthogonal matrix similar to 2, it's the same concept, except the eigenvalue corresponding to the eigenvalue -1 is the axis about which the rotational matrix acts. And this will be perpendicular to the plane across which it is reflected upon. So this is, I think, pretty intuitive. And one useful exam trick you can consider here is that if you have a matrix A and say every row of the matrix A sums to some constant, then we can check V to be some vector, 1, 1, 1, is an eigenvector of A with eigenvalue lambda, right? So for example, AV is equal to lambda V, where in this case, our V here could be something like 1, 1, 1 if it's 3-dimensional. And this is very useful because for a 3x3 orthogonal matrix, if the lambda value is equal to 1, this may immediately identify the axis of rotation, which in this case would just be 1, 1, 1, right? And if lambda is equal to -1, then this may immediately identify the direction perpendicular to the planar reflection. So I guess that's just something you could check out during when you're doing the problems, right? So I guess that can be applied to, for example, a matrix here. If you, I guess, sum these elements, right, they should all be able to achieve the same sum. And you can use this very useful trick here. Okay, so for this example, we want to give a geometric description of the matrix A. This is basically just, I guess, kind of what we talked about from before. The first thing you want to check with these types of example is whether the matrix is orthogonal. So recall that it's orthogonal when A transpose A is equal to I, right? But I guess in an exam, you don't really want to multiply a 3x3 matrix by a 3x3 matrix. That's kind of annoying. So one little hack you can do is just look at the respective columns of a matrix A. So if you have A1, A2, A3, which is just our columns of the matrix, you can check that the magnitude of each of those vectors is equal to 1. And also note that the respective dot products between each column would be equal to 0. And because it's equal to 0, this implies that they are orthogonal to each other. Because each vector of the column has magnitude 1, and they are orthogonal to each other. You can say that the columns of A are orthonormal, so therefore A is orthogonal, right? So this is much, much better than multiplying a 3x3 matrix by a 3x3 matrix. Okay, so now you kind of just have to check the determinant. Kind of a tedious process. I don't think that's like really a shortcut to it. But if you check the determinant of this, you should get that this is equal to 1. And because it is equal to 1, therefore A is a rotation. Okay, so this is kind of like the trick I talked about from before, right? If you consider some vector 111 and you sum it into AV is equal to lambda V, you should be able to get that lambda is equal to 1. So you can directly say that the axis is just 111, right? And because it's a rotation, you sub it into the trace formula. So you get that 1 plus 2 cos theta is just the sum of the diagonal entries. So these three things here. And obviously remember the scalar in front of the matrix. If we sum those three elements up, you should get that this is equal to -1. And you kind of just rearrange and do a trig and find that your theta is equal to 180 degrees. So I guess your geometric interpretation of this would just be that A is a rotation by 180 degrees about the axis of vector 111. Any questions? Yeah, I think this is pretty straightforward. Okay, so this is a very, very neat trick. I actually didn't know this when I did this back in 2601. But yeah, Kevin found this, and this is really nice. You can like check your answers using this. So this is just kind of a speedrun trick. If you consider this, I guess like orthogonal matrix Q, and then if Q is not symmetric, the axis of rotation is along this thing here. And the fun fact about this is that the angle of rotation, say theta, satisfies this form here. And this method is very nice because it also works for rotor reflections. So if Q is equal to Q transpose, its axis of rotation is any non-zero column of this form here. And the angle is either 0 degrees or 180 degrees. Again, I don't think Sean taught this in the lecture, but then this trick is very nice because you can kind of use it to check your answers. But yeah, just something, I guess, interesting to know about. Okay, now moving on to conics. So conic is a section, is any curve in a two-dimensional space whose general equation contains the expressions of degree almost 2 in the variables x and y, right? And we kind of classify conics by the sines of x squared and y squared. I'm not going to go too much into it because I think you have seen this in like high school, but basically if the sines of a square turns out positive, it's an ellipse. One positive, one negative hyperbola, and if one of them is positive, the other one is 0, it's a parabola. Now moving on to the more important stuff. So if we suppose a conic is in the form of, I guess, some quadratic equations, we can rewrite it in the form phi transpose AV and equate it to be equal to some scalar value d, right? Where phi is just, I guess you can say xy, which is an element of a two-dimensional space, and A is in this form here, which is a symmetric matrix. So note that in here the eigenvalues of A can actually be used to kind of determine the shape of the matrix, right? So if the two eigenvalues are positive, it's an ellipse. If one of them is positive, the other one's negative, it's a hyperbola. And if one of the eigenvalues is 0, then it's a parabola. Note here that the asterisk here just means it could be any sign. Okay, so now we suppose that lambda and mu are some respective eigenvalues. Because we know that A is like symmetric, the corresponding eigenspaces, they also have to be orthogonal, right? And if we set up this thing here, we can write out D to be lambda x squared plus mu y squared. I don't think you'll need to know this derivation in the test. Probably just need to know this result here. Okay, and now moving on to our first example for conics. So if we consider this thing here, and we want to find an angle such that the rotation eliminates the xy term, this question is just kind of tedious. You just kind of sub things in. So if you sub in your x and y into like this expression here and rearrange it, and then find the coefficient of xy, you should be able to equate this to be equal to 0. And if you simplify everything, you should be able to get that tan theta is equal to half. So yeah, just a bunch of like rearranging stuff. This part is a bit more important. So after rotating and translating the coordinate system, we want to write the conic in the standard form. So this is the conic we are given, and obviously we want to find our A matrix, which is symmetric, right? So 5, our coefficient of 5 will go here, and the coefficient of y squared of 2 will go here. And because we have the full xy here, remember that we have to divide it by 2, so 4 divided by 2 is 2, so that's where these two terms came from, right? And if you do the determinant of A minus lambda identity and equate it to be equal to 0, you should get that the eigenvalues are equal to 6 and 1. And I'm not going to go too much into this, but if you, I guess, determine the kernel of the corresponding eigenvalues, you should be able to get that the eigenvectors are these two terms here. Because for P, we kind of want to like normalize each column, we divide these two vectors by square root of 5, because 1 squared plus 2 squared is 5. And you should be able to combine these two vectors and get this matrix here. Okay, and this is just a continuation. So we know from before that we have to set V to be P multiplied by some vector W, right? If we set our V to be some vector xy and our W to be, I guess, capital XY, we have this expression here. And if you expand the right-hand side, you should be able to get lowercase x in terms of some capital X, in terms of some expression in capital X and Y. And you can also get the same for lowercase y as well. So if you sub this back into the conic expression, again, just a bunch of tedious algebra, I'll just leave it for you guys to do yourself. You should be able to get this expression here, which is basically just an ellipse if you rearrange it. Okay, so that's kind of the tedious stuff out of the way. Now we're moving on to determining the center and principal axes in the original xy coordinate, right? So if you look at the thing from before, you know that the center has to be at square root of 5 over 2 and 0, right? You just look at these two expressions here. So because you know that the center is square root of 5 on 2, 0, you can't just sub it into this expression here, and you just expand out the matrix to kind of convert it into the xy coordinate. So that means that the center is just 1/2. Okay, so again, it's just very similar stuff, except now you have the 1, 0, and 0, 1. You once again just do a bunch of matrix multiplication and to convert it into the original form. And you should be able to kind of extract the directions of these two vectors and say that they are these two right here, which will be our principal axes in the original xy coordinate plane. Any questions? Okay, so now moving on to singular values. So singular values is only applied to MATH2501, so I guess if you do 2501 you can temporarily just take a break. So basically we have two definitions. We say that a singular value of an m by n matrix A is basically just the square root of the eigenvalue of A adjoint A. So that means that, right? Where sigma is basically just the singular value and lambda is our eigenvalue. Okay, and then for our definition 2, we actually want to determine the singular value decomposition. So basically our SVD for an m by n matrix A is a decomposition of the form A use sigma V adjoint, where U is basically just an m by n unitary matrix and V is an n by n unitary matrix as well. And sigma here is also a m by n, is an m by n matrix of the entries of these two here. Where now here that whenever I is not equal to j, obviously you'll have the entry 0. So I think the best way about this is to just kind of go to an example, just to make it a bit clearer. But generally the way to, like, I guess find the respective components of the SVD would be to first kind of find all n eigenvalues of lambda I of A adjoint A, and then write them in descending order, which you probably would have seen in class, right? So then you would also find the associated eigenvalues of unit length Vi, and then you would use that to compute your Ui, which is just given by this formula here for each non-zero eigenvalue. And from there on you can kind of extend it to some orthonormal basis, either using cross product or this here. So our form UV form from our columns Ui, Vi respectively, and they form sigma from the singular value of this stuff here. So I guess now we can move on to a lemma. This is kind of just used to speed up step 1 by just a little bit. So if you consider A adjoint A adjoint, they must share the same non-zero eigenvalues, right? So what you can say is if the rank of A is equal to Q, then A adjoint A has Q non-zero eigenvalues. And from there on you can just conclude all the other eigenvalues are just equal to 0. And this is very, very useful when n is greater than m, because A adjoint A is an n by n matrix, whereas AA adjoint is an m by n matrix. So you can quickly determine, I guess, the eigenvalues which are not 0 from there. Okay, so once again, these types of like theories, it's probably easily demonstrated in an example. Okay, so what you can first consider is some matrix A of this here, and you kind of, this question is nice because it kind of guides you into finding the SVD, right? So obviously the first step would be to find the eigenvalues of AA adjoint. I've just written it out, but basically you should be able to get this matrix here at the end. And from here on you want to kind of find the two eigenvalues, right? So you just consider that A minus lambda I and set it to equal to 0. So if you consider the trace, which is just like lambda 1 plus lambda 2 is equal to 22, and the determinant, which is just lambda 1, lambda 2 is equal to 1 120, you can kind of rearrange it to find your lambda 1, lambda 2. But this example is kind of nice because you can kind of see it by inspection that automatically lambda 1 is equal to 12 and lambda 2 is equal to 10. And then part 2, very straightforward. Like from our theorems from before, I've said that A adjoint A and AA adjoint would have the same non-zero eigenvalues. So that means that 12 and 10 are eigenvalues of A adjoint A as well. And the remaining eigenvalues must be 0. So for part 3, you just want to compute A adjoint A. Again, it's just a bunch of tedious algebra, just matrix multiplication. And then from here on, you can consider that for lambda is equal to 12, you want to kind of put it in this form here to find this corresponding matrix. A quick tip you find from this is that the third row must reduce to the 0 row, since 12 is indeed an eigenvalue. So we just need to satisfy the equations of the first 2 rows. So if you consider the kernel of this matrix here, you should be able to get this vector here, which will be our v1. And we also do the same thing for the other eigenvalue. So for eigenvalue of 10, just consider A adjoint A minus 10i. And once again, just consider the kernel of this matrix, and you should be able to get that the corresponding eigenvector is equal to minus 2, 1, 0. Lambda is equal to 0, once again, same process. You consider like this thing here, except now your lambda is 1, right? So you sub it in and you consider the kernel, and you should be able to get that the corresponding eigenvector v3 is equal to this form here. Okay, so now that you have all v1, v2, v3, you want to normalize it, right? So you can just divide each vector by the corresponding magnitude to get the unit vector. And then to find the corresponding columns of U, you can just consider 1 on square root of lambda, AV. And once again, just kind of sub it into the formula and do a bunch of matrix multiplication to get these 2 vectors here. And from these 2 vectors, you can combine it together to form a matrix U. And you also do the same for this here. This is just your singular values from before, right? So because our eigenvalues are 10 and 12, you can just take the square root of them and put it in descending order to get this diagonal here. And the reason why we have the 0, 0 at the end here is to just kind of match up the dimensions so that the form actually works. And of course here, it's basically just the normalized vectors of v1, v2, v3 that you have seen from before. But yeah, pretty straightforward. Any questions? Okay, so now moving on to, I guess, some more interesting stuff. So here's like a reduced singular value decomposition. So if we consider some, again, same matrix, right? We can say that the reduced SVD of A is in this form here, where you basically kind of just reduce each one to these dimensions. And note here that this here is diagonal and invertible, and that the columns of these 2 are obviously orthonormal. Right, so if we look at the previous example, we know that the rank of A is equal to 2, and you would note that our original sigma is this thing here, right? But because we kind of want to like subtract 1 dimension, you just remove the 2 zeros at the end. So you're left with a 2 by 2 matrix. And then same for our V here, we kind of just want to remove the last row. And that is simply because our rank is 2, and 3 minus 2 is 1, so you want to remove the last column. Okay, and now moving on to pseudo-inverse. So if we are given some reduced SVD of this form here, as you have seen from before from this example, we say that this thing here is the pseudo-inverse. So this is pretty straightforward. You can't just take the inverse of the sigma and you just put it in, and once again just do a bunch of computations to get this matrix here. Any questions? Okay, so now we want to look at SVD kind of under orthogonal transformations. So here our Q matrix is some 4x4 matrix and our R is some 3x3 matrix. And we'll let them both be orthogonal. And we want to prove that B and QBR have the same singular values. Okay, so because we know that Q and R are orthogonal, it means that Q transpose Q has to be equal to the identity matrix. Similarly, our R transpose R is equal to the identity matrix as well. And note that because they are orthogonal, this here is also equal to our identity matrix. Okay, so now you can just kind of sub things in. So if you sub in A to be QBR, you should be able to simplify this expression here. And here, because you're applying the transpose, you kind of just, I guess, reverse the direction of this. So it'll be R transpose B transpose Q transpose, right? And because your Q transpose Q is equal to the identity, that kind of just becomes I. So you're left with this expression here. Okay, and since you know that your R transpose is equal to your R inverse, because once again I just times, I guess, both of these by R inverse, you can once again just rearrange everything to get this form here. But yeah, this question is kind of nice because it kind of hinted at you. Yeah, they already gave you hints from the question. And just kind of have this sub things in and force it to work. Okay, so what we have proven is that A transpose A is similar to B transpose B, right? From this expression here, which implies that they have to have the same eigenvalues and singular values as well, because singular values are just the square root of the eigenvalues. And this also includes their corresponding multiplicities. Okay, so this is just kind of a bonus question. This one's a bit harder. So if we suppose that Vi is the right singular vector of B associated with the single value sigma I, and Ui is the corresponding left singular vector, then these two are true. So if we define this to be Qu and this to be R transpose V, you can check that your AV is just equal to, you just sub this in, QBR R transpose VI, right? And because R transpose is just equal to the identity matrix, that kind of just cancels out. So you're left with this form here. And after a bunch of simplifying, you should be able to get this. Same trick here, you do A transpose U, you sub things in, and you get that Q transpose Q is equal to the identity matrix, so that kind of just goes away. So what you're left with is R transpose B transpose U. And once again, just kind of sub things in and you get this form here. So what can you say from these two things is that the left singular factors are QUI and that the right singular factors are R transpose V. Any questions? Okay, no? I guess we can move on. Okay, so that's kind of geometric properties out of the way. Now we're going to move on to canonical Jordan forms. So starting off with the Cayley-Hamilton theorem, we say that for any matrix A, which is an element of a P by P matrix, this is true, right? And here we kind of just have an example. So if we consider some polynomial to be in this form here, and we want to suppose that phi is some element of the image of t squared minus 4t plus 6i is non-zero, we kind of want to use the Cayley-Hamilton theorem to prove that phi is an eigenvector of t with eigenvalue of 1. So this question is actually not too hard. If you consider the T of V, it would say that is equal to 1v, right? So we can kind of guess that the quadratic is a factor of a cubic firstly. So if we sub in, like, for example, 1 into this, you should be able to get 0. And from there on, you can just kind of factorize the polynomial out. So this shouldn't be anything too new. So note that if v is an element of the image, we can write that as this form here. And then by Katie Hamilton, we know that this thing here is just equal to that. And you kind of just simplify everything. And in the end, you should be able to get that this implies v is an eigenvector with an eigenvalue of 1. So that's kind of pretty intuitive. Okay, so now we're moving on to the power series. Okay, so because like a polynomial can be kind of written when applied to a matrix, provided that constant term c is equal to ct naught in pt are interpreted as this one here, we can kind of define convergence in terms of some matrix of norm of something. So some options you have seen in the lecture would be the Frobenius norm, which is basically just taking the square root of the trace of A adjoint A. You also have encountered something called the infinity norm, which is basically just, I guess, taking the maximal distance. And then you also have the operator norm, which is very similar to the infinity norm, except now the norm of V is equal to 1. Okay, so now moving on to Jordan blocks. So we say that a k by k Jordan block for lambda is of this form here, where basically the diagonal entries are always lambda, and you just kind of put 1 above each corresponding lambda, and that's called a Jordan block. So here are some quick examples. If you say J3 of -4, obviously it's going to be a 3 by 3 Jordan block, so this is why this is 3 by 3. And because it's of -4, the diagonal entries are -4 along the diagonal, and then you just put 1s above each -4. So same thing here, J4 of 0, except now your eigenvalues are 0, so you kind of just put the zeros on the diagonal entries, and you put 1s above each corresponding 0. Okay, now moving on to the powers of Jordan form. So Jordan forms are very, very nice because you can kind of, I guess, apply powers to them, and they kind of work out as binomial expansions. So, for example, if you like apply this to the n, you just get lambda to the n, and if you get apply this to the n, you get like lambda to the n plus n choose 1, lambda to the n minus 1, and you get lambda n here. And this works for like any case. So you can apply this to really any, for example, m by n matrix. So yeah, this is just kind of reinforcing what I said before. So if we start with lambda n on each diagonal entry, we can put like n choose 1 lambda to the n minus 1, where we can immediately above lambda n, and then also do this for n choose 2 lambda to the n minus 2, wherever you can immediately have like above n choose 1 lambda to the n minus 1. So this is just what you have seen here. Like the diagonals, they kind of match up. Like this here. Oh yeah, and like an important note is that if you ever like bump into n choose n, that has to be your last entry. Okay, so now moving on to the direct sums of matrices. So if we have some direct sum of matrices A1 all the way to AN, we can say this is the matrix formed by putting, I guess, these matrices on the diagonal and zeros everywhere else, right? So it would look something like this. And when you see like a matrix with like diagonal entries like this, we say that this is the direct sum of the corresponding matrices. Okay, so I guess an important note, in this course we only worry about this with Jordan forms. and orthogonal transformations on real finite dimensional linear product spaces. You can check the lecture slides if you want. So here is a quick example. So yeah, pretty straightforward. You have J2 of 3, so that means 2 by 2 Jordan block with lambda is equal to 3. Right? And then you also have J4 of 5, which is just a 4 by 4 matrix with eigenvalue of 5. Right? So this is pretty straightforward. Okay, so now we want to look at the powers on the direct sums of Jordan blocks. So basically the power of a direct sum of Jordan block is the direct sum of the powers of Jordan blocks, of each respective Jordan blocks, right? So if you have this to the n, you can apply this to the n to all corresponding respective Jordan blocks. So this would be kind of like an example of what happens. So if you have the direct sum of these two Jordan blocks here, you can apply this power to each of them, right? And you will see that it would look something like this. Okay, so now moving on to generalized eigenvectors. So we say that the generalized eigenvectors corresponding to the eigenvalue lambda is some non-zero vector v satisfying this property here for some integer k is greater or equal to 1. And this kind of differs from the usual eigenvector in the sense that those must satisfy these conditions here. So for example, we must take k to be equal to 1. So here's just a quick example. We are given some 3 by 3 matrix C and some vector 1, minus 2, minus 3. And we want to show that the matrix C, that for the matrix C, phi is a generalized eigenvector corresponding to lambda is equal to 5. So yeah, just like what you typically do, you just do your matrix minus 5 times your eigenvalue to get this matrix here. And then you can't just continuously left multiply to b, right? So if you do C minus 5 by, C minus 5 by multiplied by our vector phi, you should get this here. But if you do it again, you'll notice that the vector becomes 0. So what that means is that phi is a generalized eigenvector corresponding to lambda is equal to 5, because you eventually reach a state where the final vector is equal to 5. And now moving on to generalized eigenspaces. So if we consider some matrix A, which is some m by n matrix, we can say that the generalized eigenspace of lambda, denoted by this here, which is just generalized eigenspace, is the set of all generalized eigenvectors of A corresponding to lambda, right? And I guess this is just how you write it out in standard notation. And note here that obviously our vector can't be equal to 0. And okay, I guess like a way you can like put this, like look about this, is to kind of consider this in terms of like kernel, because you can see here that phi is basically just the kernel of this thing here, right? So obviously you can write this as like the union of the kernels of all of these. But yeah, that's like pretty straightforward lemma from that. Okay, so Jordan matrix. We have seen this from before, is basically just the direct sum of respective Jordan blocks. And we want to kind of, in a way, mimic diagonalizable matrices as much as possible. So the Jordan form of a matrix will become its complete similarity invariant. And we also know that every matrix A has one unique Jordan matrix up to some permutation, which is a very useful property in proving a lot of things in linear algebra. Okay, and now moving on to an example. So if we consider some 4 by 4 matrix A, and we are given that f of x is equal to some random cubic, we want to kind of determine the eigenvalues of f of this matrix without calculating it, we can kind of just consider f of a, right? And then just sub our matrix A into the function. So if you sub it in, you should be able to get this form here after expanding it out. And know that because AV is equal to lambda V, you can convert all of these terms into some variation of lambda to the n multiplied by our vector V. Right, and you can obviously convert it back. You can say that this is equal to f of lambda multiplied by V. So what is left is now just subbing in the eigenvalues, right? So if you sub in the eigenvalues 2 and minus 1, you should be able to get 5 and 2. And because you get that they are equal to 5 and 2, this implies that they are the eigenvalues of f of a. Any questions? Nope? Okay. So here are some useful properties. Yeah, but these are very useful in checking whether you made a mistake during the test, I guess. So if you consider some nullity a minus lambda I to the k to be denoted by dk, and our d naught is equal to 0, which is also equal to the nullity of a minus lambda I to 0, then we have that the kernel of a minus lambda I to 0 is obviously a subset of each correspondingly higher power, right? And then because you denote your dk to be equal to this, you can kind of write this as d naught is less or equal to d1 and continue that there. And from this is just basically a consequence of that. You can just kind of take the difference between each respective dk and say that this is true. So what you should note here is that the nullities must not decrease and the difference in nullities must also not increase. So here's a quick example. So if you consider some matrix C, which is some 3 by 3 matrix, and you want to find the eigenvalues of C, obviously you consider the determinant of C minus lambda I. So if you find the determinant of this minus lambda I, you should get this cubic here. So then you can just kind of factorize things out and equate it to be equal to 0 to find what lambda are. And after you equate it to be equal to 0, you should get that the eigenvalues are equal to 3 and 5. So now let's just take a look at the two eigenvalues. So I guess what we can do is start off with lambda is equal to 3. So if you start off with lambda is equal to 3, just kind of consider c minus 3i, c minus 3i all squared, c minus 3i all cubed to find these matrices here. And here, after you determine this one, you kind of just want to row reduce it to make our life a bit easier. Because from this, you'd want to kind of find the kernel, right, to find the corresponding factors. And similarly, you do the same for lambda is equal to 5. So consider c minus 5i, c minus 5i all squared, c minus 5i cubed. Obviously, after you find it, you want to row reduce it. And then from here on, you can just find the kernel of each corresponding matrix. Okay, so note here that for lambda is equal to 3, the nullity at each step was 1, 1, 1. And you can see from here, right, because this here, the rank is 2, so you're just left with this, and then same here, and same here. So this clearly obeys the theorem that nullity should be non-decreasing. And we also know that the differences in nullity should also not be increasing, right? Because the difference between ones is just 0. So that satisfies that property. Okay, now moving on to lambda is equal to 5. The nullity at each step was 1, 2, 2. So yeah, that makes sense because the rank of this 2, so nullity is just 1, right? And then here nullity, the rank is 1, so nullity is 2. Here the rank is 1, nullity is 2 as well, so it's just 1, 2, 2. Again, it clearly obeys the theorem, right? Because the difference between 1 and 2 is just 1, 2 and 2 is 0. So it's not increasing. And also note that the nullities kind of seem to terminate at a maximum value. So if we look at lambda is equal to 3, it's 1, 1, 1, right? So it seems to kind of terminate at 1 and doesn't go any higher than that. And for lambda is equal to 5, we can see that it can never go higher than 2. So that's just kind of an important thing to remember during the test. And obviously this is exactly equal to each eigenvalue's algebraic multiplicity. Okay, so moving on to minimal polynomials and the Jordan form. So if you consider once again some square matrix A, the monic non-zero polynomial of the smallest degree for which A is a root is called the minimal polynomial. And for 2601, your typical notation is this here. So I guess whenever you see that, just think of minimal polynomial. And I guess the key relationship is basically, if you suppose lambda is some eigenvalue of A, then the exponent of t minus lambda in the minimal polynomial, right, is equal to the size of the largest Jordan block corresponding to that eigenvalue. So you can kind of write it in this form here, right? And then you can say that the largest Jordan block corresponding to the eigenvalue lambda I is of size ki. So this is just kind of a useful exam summary. A characteristic polynomial, which you have seen from I think part 1, gives the total size of Jordan blocks. And then your geometric multiplicity is the number of Jordan blocks. Your minimal polynomial, as I said before, is just the size of the largest Jordan block. And then now moving on to diagonalizability, we say that these three conditions are equivalent. So if A is diagonalizable, then obviously each Jordan block of A has size 1, right? Because it's just diagonal entries of the eigenvalues. And then we also say that a minimal polynomial also has distinct linear factors. But yeah, pretty straightforward. And this is just kind of an example you could kind of do. So if we are given some A matrix, which is 6 by 6, and say it has 2 as one of its only eigenvalue, and we suppose that this is true. We also suppose that dimension of the kernel is equal, dimension of the kernel of this is equal to 3, which is also the same as, the nullity is equal to 3. We want to determine the Jordan canonical form of A. Then we can just, I guess first what we can know is that because 2 is, I guess, its only eigenvalue, its algebraic multiplicity has to equal 6, right? So what I can say is that the sum of the sizes of the Jordan blocks correspond to lambda is equal to 2 is 6. And because the minimal polynomial is t minus 2 to the 4, the largest Jordan block corresponding to lambda is equal to 2 is just the power of this, which is just 4. And then if we consider the dimension of the kernel of A minus 2i, this is equal to 3. So what that means is that there would be exactly 3 Jordan blocks. So because we kind of require 3 Jordan blocks, what we can say is that we require the sum to be 6 and the largest size to obviously be equal to 4, right? So if you think about it, the only possibility is 4 plus 1 plus 1 is equal to 6. So this would be what your canonical form of A is. Again, your J4 of 2 is just this thing here. Your J1, 2 is just this, and then same with this. So you just kind of combine everything together and make it into one giant matrix. Any questions? Okay, no, I guess we're moving on. Okay, so now moving on to multiplicities. So if we consider the dimension of the generalized eigenspace of lambda, of eigenvalue lambda, this is equal to the algebraic multiplicity of lambda, right? And this really only implies that we only ever have to compute this here up until its nullity equals the algebraic multiplicity of lambda, right? Because obviously it always terminates. Okay, and this is just kind of a nice little relationship between AM and GM. Obviously your geometric multiplicity has to be greater or equal to 1. And the reason for that is because your eigenvector can never be equal to 0. And we also know that our algebraic multiplicity also has to be greater or equal to our geometric multiplicity. So I guess like in an exam, if for some reason this is larger than this, then you have obviously stuffed up somewhere. And yeah, this is just a fun fact. Obviously the GM is just the nullity of A minus lambda I. Pretty self-explanatory. Okay, and now computing Jordan matrices. So fast way you can go about this is to just consider Jordan chains to find the matrices P and J such that this form here is true. So for an eigenvalue lambda with algebraic multiplicity of k, we kind of need to start with some factor Vn such that for each ongoing multiplication, we get that this is true, right? And then we then need to include this to pk. So this, after you do all of this, you can just combine everything together, and that would be known as like one Jordan block in the direct sum of your main Jordan block, your main Jordan matrix J of A. And you kind of want to do that for every single corresponding eigenvalue. And this is just, I guess an easy way you can go about this is to just consider block diagrams. So the nullities at each step, so aka the power of A minus lambda I to the k. And then we also want to consider Jordan chains that can be formed and the overall structure of the contribution of each eigenvalue to the Jordan matrix, right? So usually for stuff like this, you will consider the difference between each corresponding entry, right? So obviously you start with 5, and then 8 minus 5 is 3, 11 minus 8 is 3, and then 12 minus 11 is 1. And you know it didn't start well because this is decreasing, right? So then you can just kind of draw in the blocks. Again, just 5, 3, 3, 1. If you draw in the blocks, you want the first row to have 5 blocks, so something like this, and then you want the second row to have 3 blocks. The third row to have 3 blocks as well, so something like this, and the last row to have 1 block. Right? So from here, you kind of just want to read it vertically. So if you look at this is 4, and then this is 3, this is 3, this is 1, 1. So hence the Jordan blocks are 4, 3, 3, 1. And you can just kind of put everything into your Jordan form. So each of these corresponding entries is basically the size of your Jordan block, right? So yeah, that's kind of nice. Like Jordan blocks, block diagrams are very useful in determining, I guess, the Jordan form of a matrix. This is an example you could try yourself. Yeah, you just kind of consider the difference between each one, right? And you want to show why is this not possible. Generally for block diagrams, you always want this to kind of like decrease in size between each corresponding row. But for this one here, it doesn't because you're going from 3 to 1 to 3. So that's not decreasing. So it's not gonna work. If you try to draw it out, you'll kind of see why. And then here it's kind of the same thing. I'll leave it as an exercise for you. You just kind of consider the differences between each one and kind of just draw in the Jordan blocks. So the first one will have like 5 blocks, second one will have 3, and the last one will have 1 block. And then you just read each line vertically to determine the size of each Jordan block. This one is just something I found online. I personally wouldn't use this, but I guess it's just nice to know because you can kind of use this formula to check whether you did things right. Pretty sure it is like slower than using block diagrams though. But if you you like consider the number of Jordan blocks corresponding to some eigenvalue of exactly size k, you can kind of use this formula here, right? And the reason for that is because, like, same concept, you're just considering the differences between each one, and if you simplify, you should just be able to get this expression here. So this is just kind of an example of how you would use that formula to find the corresponding, like, sizes of the Jordan form. So for example, size 1, you would do 2 times 5 minus 8, because you would consider D1 and D2, and then size 2, 2 times 8 minus 5 minus 11, because you would have like these 3, right? And you would do it for up to size 4. So therefore the Jordan block sizes are 4, 3, 3, 1, 1. But yeah, once again, I probably wouldn't, like, this would not be the first thing I'd do. I'd probably like consider block diagrams first, and then maybe if I have time after the exam, I would use this to check. Okay, so now moving on to another example. I'm gonna skip part 1. I'm pretty sure you guys can just do it yourself, right? You just compute the matrix and multiply them together. And then for part 2, we want to, without any matrix calculations, write down all the eigenvalues of C and the algebraic and geometric multiplicities, and we also want to give reasons for our answers. Okay, so the easiest way to go about this is to, I guess, consider the trace, which is is just the sum of the eigenvalues, right? So if you take the trace of this matrix, you get 9 plus 2 plus 2 is equal to 13. You also know from like part 1, 5 is an eigenvalue of C with algebraic multiplicity of at least 2. So because you know that 5 appears 2 times, and you're just left with one remaining eigenvalue, let's say lambda 3, right? So you can just add them up together and equate it to be equal to 13. If you move the 5 plus 5 over, you should get that lambda 3 is equal to 3, which obviously is the remaining eigenvalue because it's a 3 by 3 matrix. So this is just kind of a summary of what we have. And then now for part 3, what was it? Okay, yeah, we want to kind of find a invertible matrix P such that this holds, right? So here it's, once again, pretty straightforward. You just consider C minus 3 times some eigenvalue 3, right? And after you do that, you kind of just want to row reduce it to make your life a bit easier when finding the kernel. So if you find the kernel of this should result in the corresponding eigenvalue of 102. And then you also kind of do the same for the other eigenvalue. So here your lambda is equal to 5. So if you just find the kernel of this in here, you should get that this is equal to that, which is just our corresponding eigenvector for that eigenvalue. And we also want to kind of do this twice. So if you do this twice, you should be able to get this, and once again, you just kind of reduce it to become this. And from here on, you want to, I guess, consider the kernel of this. You would find that this is just equal to the span of these two vectors. And from there on, you kind of want to do your Jordan chains, right? So what vector do you start with? You want to look at this, and you want to pick a vector that's in this, that is not in pick one vector in this that is not in the kernel of C minus 5i for it to work. So in this case, I picked 1 minus 2 minus 3. So after I picked 1 minus 2 minus 3, I applied C minus 5i to the matrix. So I times C minus 5i to 1 minus 2 minus 3. I I get this matrix, this vector, and then I do it again, and eventually I get 0. And this one is just the vector corresponding to the other eigenvalue. Obviously, because it just occurs one time. If you apply this matrix to this vector here, you would obviously get 0. So that shouldn't be too big of a shock. Okay, so now you've kind of done the hard part. You now want to put this in the Jordan form. So our first block will be this here, because our eigenvalue of 5 occurs 2 times. And then you're left with 3. And then now you just kind of want to put what you computed using the Jordan chains. You start off with 1 minus 2 minus 3. So you put this at the end, and then you're left with minus 1, 1, 1. So you put this at the beginning. So you kind of like read it backwards, and then just put it in the Jordan form. And obviously you're left with this vector here for the corresponding lambda is equal to 3. So just chuck it in, and you should be able to get your matrix P. Okay, so now moving on to, I guess, another example. So we want to find the Jordan chain for lambda is equal to 2, starting with 0, 1, 1. Again, pretty straightforward. Start with some random vector and just apply a minus 2i to the vector. So a minus 2i, 0, 1, 1, and you should be able to get this matrix, this vector, and you once again do it again to get this. So it terminates there. And then for part 2, without any calculation, we would kind of want to write down the GM of lambda is equal to 2 and want to give reasons for our answer. Okay, so we know that our GM has to be less or equal to 2 because once again, AM is equal to 2. But we know that GM cannot be equal to 2 since we have a chain of length 2. So that implies that GM has to be equal to 1. And this here, you just kind of chuck everything in. And yeah. This, I think I'll just leave as an example for you guys. You basically just consider V to be some element of the generalized eigenspace of 2 and W to be some element of the generalized eigenspace of lambda value 3, and you kind of want to find a vector such that this condition holds. You can kind of just consider the span of each of those and apply scalar multiples to each one to find what V and W are. But yeah, I'll just leave it up to you guys. Okay, and this is just a little theorem. So we say that the direct sum of generalized eigenspace of any A of n times n matrix is C to the n. And I guess like in an exam, you want to kind of check your answer. So in order to do that, you can just kind of move this over and check whether this thing here is true. Just to check whether you made any silly mistakes. And this is basically easier than computing this directly because you don't have to find P inverse. Okay, and now a remark on finding Jordan chains. So sometimes they don't always give you the starting vector, which is kind of annoying. So for example, like this is from the 2021 finals. Yeah, so as part of the working out, we had to cook up our own starting vector, right? So in the question, I think it was given that there's like a Jordan chain of length 2 for eigenvalue of 2 for the following matrix A, right? And from here on, they wanted us to find the vector ourselves. So if we consider A minus 2i, we get this matrix here. And we kind of want to find some vector phi2 such that this condition holds. So I guess what you can do from this is to consider kernel of A minus 2i all squared. And you also want to consider the kernel of A minus to I, right? If we pick a vector such that it belongs in this, but like in this, but the vector is not in this, then we know that our v2 works, right? And then you can also check using this in here. So you just times the matrix by v2 to check that it is equal to v1. And then once again, you times the matrix by v1 to check that is equal to 0. Okay, so now moving on to our last topic, which is matrix exponentials. So in general, for a square matrix A, which is M and N F, the matrix exponential form is given by this expression here. And we usually write this as, I guess, a Taylor series of e to the A. So this is just like how you would do it for like normal numbers, except now your x is like a matrix. And here are some properties. Just like our numbers, we can kind of write the product between the exponentials of a and b to be equal to the exponential of the sum of a and b. And note here that this only works when a and b commute. So do not do this if they do not commute, because it won't work, right? And we also know that the inverse of exponential of a is just equal to exponential of minus a. So you can just kind of sub in the minus sign. And this is also like kind of the same thing. If you apply the derivative to the exponential of some matrix A, you can kind of like chuck the A out and say that it's equal to A exponential to A. And of course, you can put this at the end as well. But yeah, pretty much the same as like normal numbers, except now you have matrices. Okay, so now we want to like calculate matrix exponentials. So if you consider A to be P inverse, then the exponential of A is, you just apply the exponential component to the matrix B, right? And we also know that if A is like the direct sum of respective matrices up to n, then exponential of A can be written as the exponential of A1 direct sum with all the other exponentials as well. So you can kind of just like separate it. And this is just like the exponential of T Jordan form K of lambda. So this is obviously just like a K by K matrix. And then you can just apply like the exponential rule to each row. This is kind of similar to what you saw before for like the binomial expansion stuff, except now it's exponential, so you kind of apply it like a Taylor series. But yeah, this is pretty intuitive. So this is just kind of an example of what it looks like when you apply the exponential to T of some Jordan form. So in here, our Jordan form is, our Jordan block is a 5 by 5 matrix with lambda is equal to 2, right? So if you apply it here, you kind of just chuck the 2 out and apply to the exponential. So e to 2t multiplied by this in here, where you recognize that each row here is basically just like your Taylor series for exponentials. So yeah, as I've said before, we're really just filling in the matrix with terms from the power series of e to t. So here's another quick example. So if we recall this in here from earlier, we kind of want to compute exponential of tc. So we have some matrix P of this form and J of this form here, and we know that if we applied our exponential to tc, we only really apply that to the thing in the middle. So if you apply it to the thing in the middle, you can kind of, I guess, like look at these two components separately and write it as the this one here. So if you apply the exponential to this block here, you should be able to get this here. And then if you apply the exponential to like this block here, you should be able to get this here. And in the end, you kind of just want to combine everything together. So if you combine everything together, you can just kind of like, again, just chuck this in and put the P inverse in as well. And if you want, you can also kind of expand it out to get the final expression. Okay, so now moving on to the column method. So basically, if we once again just have a bunch of Jordan chains, we can say that the exponential is equal to this in here. So essentially, you just once again just extract the eigenvalue out and put it as a power to the exponential. And here you're just left with the power series, kind of, where each one has like the corresponding factor that you got from your Jordan chain. Okay, so this is just kinda an example, right? So if we consider our matrix A here, which basically just has a Jordan block of J2, J2 of 2 and J2 of 3, so lambda values corresponding to 2 and 3. For lambda is equal to 2, we have this here. So yeah, basically just what you have seen from before, right? You start with some random vector and you apply A minus 2i to the vector to get your V2. And then obviously because it's just a 2 by 2 block, you're gonna terminate after the second one. And then you also do the same thing for lambda is equal to 3. So if we, for lambda is equal to 3, yeah, once again, the same concept. We start with some vector 0, 0, 1, you apply your A minus 3i to the vector, and you should be able to get this. And once again, because the block is 2 by 2, if you apply again, you should be able to just get 0, right? And from there on, you can kind of just apply e to the ta of v1 and e to the ta of w1 as well. And this becomes e to the t v1 plus t v2, and this becomes e to the t w1 plus w2. And from there on, you just kind of once again combine everything together, which you have like seen from before from this, right? So if you put this together, you should be able to get this block from this, and you should be able to get this block from this. Okay, so any questions? I think I went through that quite fast. If you have any questions, please stop me. Okay, so now moving on to solving homogeneous systems of differential equations. So once again, we can kind of compute exponential ta multiplied by some factor phi for some factor phi without actually having to compute the exponential matrix, right? By using the column method we have discussed from before. So using that, we can kind of use the same concept to, I guess, find the solution to differential equations. So we say that the solution to dy dt is equal to ay with the initial condition y naught is equal to c is given by this here. And this is just kind of an example that we could see, right? So if we record the matrix C, which is some 3 by 3 matrix, and our factor phi, which is 1 minus 2 minus 3, and we have this Jordan chain here, we can kind of use this to solve the initial value problem of y dash is equal to cy and y of 0 is equal to v. So for this solution here, you kind of just can say that y of t is equal to e to tc y of naught. And that's because that's just dy on dt, and if you rearrange it, obviously it's just an exponential solution, right? And because you know that your y naught is just equal to your vector v, you can just sub that right in as well. So one thing you'll note from this is that since v belongs to the Jordan chain for lambda is equal to 5, you can just kind of apply this again to the value v and do it until it terminates, right? And because you know that v only belongs to the Jordan chain for lambda is equal to 5, you don't really need to check for the other eigenvalue. So even though I think this matrix it had like a lambda value of 3 as well, you don't really need to check it because it's not in the same thing. So only lambda is equal to 5 is needed. And this is just basically chucking everything together. So if you wait, do I have the, yeah, so for your first vector you have 1 minus 2 minus 3. You can just put that here, and then you kind of just want to add t of c minus 5i of v again. So your minus 1, 1, 1 would just be this vector here. So you can just kind of put it together, multiply it by t, and add them up together to get your final solution. I think in the lecture slides you guys also learn about like inhomogeneous cases, but I don't think that's tested. And yeah, that's the end. Any questions? Okay, thanks for coming.
Use sign-up sheet.
Sign up sheet. Oh my gosh.
You still haven't eaten your food.
Yeah, I know.